Start recording. All right, so hi everyone. We're going to continue today with the third lecture by Flaminia Giacomini. She's going to be talking about quantum information tools at the interface between quantum theory and gravity. So this is the third lecture that we had this week so far. The lectures are being uploaded to our website, both the video and the slides, so you can keep following things there if you don't quite understand what's going on, or if you want to review some of the things before the next lecture. As a reminder, you can ask questions during the talk on the Q&A chat. We're going to moderate them. There's going to be a break in the middle, more or less, so you can actually talk directly with Flaminia in additional session at the end. Thanks again, Flaminia, for joining these lectures, and it's all yours. Thank you.
Thanks. And thanks to you all for coming and organizing. Today, this is the third lecture. So again, as a recap, in the first lecture, we saw some theory-independent tools like generalized probabilistic theories and indefinite causality. Yesterday, we looked at the gravitational physics of quantum objects. So mainly thought experiments and how to describe the gravitational field in the quantum regime in the low energies when quantum systems sorts a gravitational field. Today, we're going to talk about quantum clocks, and in particular about quantum clocks as probes of probes of non-classical spacetime. So I will just build up towards that, and I will start really from the basic definition of a quantum clock, and then I will review some results that are in classical spacetime that are very helpful for us to get intuition and understand how the inner workings of a quantum clock, especially when it is put in some gravitational field. And then I will go to quantum clocks in non-classical spacetime. So let me just start with the very basic definition about quantum clocks and how they work in classical spacetime. And at the end of this, I want to understand the question: how do quantum clocks encode information about spacetime? So first of all, what is a quantum clock? So a quantum clock, the very basic definition of a quantum clock that will be sufficient for what we're going to see today is a two-level system. What is a two-level system? So it is basically a qubit. Now we know what a qubit is, that has two different energy levels. So it has two different states that correspond to two different energy levels, where we have a ground state and an excited state. And a fundamental feature for the system to behave as a clock is that its initial state cannot be an eigenstate of its Hamiltonian. So what happens? If imagine that, for instance, we initialize the system in just E0, then when we evolve this system, so the initial state E0 with this Hamiltonian, the system just acquires a global phase. And as we know, global phases are not measurable. We saw that in the first lecture. Instead, if we initialize the system in a quantum superposition of its two energy eigenstates, then when I apply this quantum evolution to the initial state, at some time t, the state acquires a relative phase. And relative phases are measurable. Now, imagine we start from this state, and we know that we start from this state. The tick of the clock can be taken as the time it takes to the clock to get to the orthogonal state to the initial one. Why? Because we know how to perfectly distinguish two orthogonal states. And this happens when this phase here is -1. So instead of having a plus here, we have that this is minus. And yeah, and this means that, so we call this time orthogonalization time. And it means that the state at this time is orthogonal to the initial state. Then we can just invert this relation and find that this orthogonalization time is pi h bar divided by the energy gap, E1 minus E0. So you see that if you want this clock to be precise, you have to increase the energy gap of the clock. So ideally, you would like, of course, this is not possible in reality, but ideally you would like to make it infinitely large, the energy gap, in order to have an arbitrarily precise clock. But if you increase the energy a lot, then what happens? That also relativistic effects start to kick in. So in particular, we know from special relativity that also the internal energy contributes to the mass of a quantum system, of just a physical system. And so in the end, even though it's a very, very small effect, when we look at it from a fundamental perspective, from a fundamental point of view, we also need to consider the internal energy of this quantum system as part of its rest mass. So effectively, what we should do is to add to the mass the internal energy of this system divided by c squared. So this means that effectively the mass becomes an operator. Now, let's see the consequences of having a mass that becomes an operator, because basically this will mean that if the clock is in some state E0, then the mass is effectively some m plus E0 divided by c squared. If the clock is in state E1, then the mass will effectively be m plus E1 divided by c squared. So if we have a quantum superposition of energy levels, we will have a quantum superposition of masses. And this is somehow a strange concept. So we can take that into account formally by simply just taking the usual dispersion relation here of a particle and then considering its rest mass in this way. So not just m, but also the internal energy of the Tisa quantum operator. Now, this system, so the idea of having a quantum superposition of masses created some problems. This was some time ago, to the point that, so I talked yesterday about superselection rules, and the superselection rules for the superposition of masses was formulated by Bergman. Let's see how this arises. And for that, we want to take an initial quantum state, psi 0. So now forget what I said about the clock. Let's just consider just a quantum state. And we want to consider translation operator and the Galilean boost operator. So a translation operator, we can represent it. So this is a translation by A. So as the exponential of I by h bar, some parameter A and the momentum P of the particle. This translates our particle by A. And then the Galilean boost is instead still a unitary operator that is the exponential of I by h bar, V sum G, where G represents the time-dependent boost operator that is Pt minus Mx. So now what we can do is to apply a cyclic transformation. So a transformation that in principle should go back to the initial state. How do we do that? So first we apply a translation by some quantity A. Then we apply a Galilean boost by some velocity V. Then we translate back by minus A, and then we boost back by minus V. So this is, you see that I am applying the one operator and then the inverse operator. So what I would expect is to have the same initial state as I started with. So I would like to have psi 0 at the end. But actually, if you compose all these operators with these definitions, just substituting A and minus A to minus A here and V to minus V here, then what you get, and this is just a mathematical calculation, it's a bit lengthy, but it's very straightforward, is that this state here goes to e to the I by h bar MAV, where A and V are these two parameters, and M is the mass of this particle. So now, in this case, this does not trouble us very much because this is just a global phase. And as we have learned, global phases are not observable. But now, imagine that we now consider an initial state which has a quantum superposition of masses. So we have a state that initially is psi0 with mass m1, psi0 with mass m2. And now we do the same transformation as we did by applying this cyclic transformation. So in front of this one, we will have a phase like that with m1. And in front of this one, of this other state, we will have the same phase, but with m2. So what we get is that for a state that is in a quantum superposition of masses, this global phase becomes a relative phase that depends on the difference between the two masses in the two amplitudes of the quantum superposition. So now something that we thought had to go back to the initial state will definitely not go back to the initial state because this is an observable phase. And this led Bergman to say that there is a quantum superselection rule, meaning that I cannot superpose states with different masses. Okay, so, however, this is also a bit strange because we superpose states with different energies, at least in the lab every day. So how do we get out of this? So formally, this, so say from the group theory perspective, this problem was solved by taking the central extension of the Galilei group. So here we just consider translations and boosts, but the Galilei group has to be extended also with the central element. So it's basically an element that is proportional to the Casimir of the algebra. So it's m, the mass of the particle, times the identity. And this should be an element of the inertial group of transformations of Galilei in order for the algebra to close. So, and that was the formal solution. However, there was still a problem of physical interpretation of this result, because what does it mean that I have to add this term proportional to the mass to the algebra in order to close the algebra? And a solution was given by Daniel Greenberger, who analyzed this actually in special relativity, but here it's the same. And so this is all without gravity, but also this argument that I gave you here is without gravity. So he recognized that this term here is actually a remnant of special relativistic proper time. So it is a special relativistic effect that percolates to the Galilean regime. And so it is no problem that there is this relative phase. It's just a fact that we have to accept, and it's just some effect of special relativity, some proper time effect that just shows up also in the Galilean regime, in the limit. So all this is to say that we shouldn't be surprised if a superposition of masses just gives us a relative phase, but it's just some normal physical effect that we should expect. Now, what does this have to do with gravity? So first of all, we needed this as a justification that having a superposition of masses when we have a clock is something that is perfectly legitimate. Then if we add gravity, now we see we will see now the rest of the story when we add gravity. So a first thing that you all probably know, but that we should just to make everything explicit, I wanted to revise, is gravitational time dilation. So, which happens also on the Earth. So let's take the Earth and let's put clocks at different heights in the gravitational field of the Earth. Now, a clock that is at some height Z1 will tick according to some proper time, tau1. But if I put a clock at a different height, Z2, because of the gravitational field of the Earth, that's in particular the G00 component of the gravitational field of the Earth, then this other clock will tick at a different rate. And in particular, the clock that is lower in the gravitational field is slower than the clock that is higher in the gravitational field. And this effect is known. Experiments measured it, and they measured it extremely precisely. So as far as I know, the record that there is now is this paper from last year, where they put atomic clocks their gravitational time dilation when they put them 1 millimeter apart, one from the other. So it's something that that people have measured extremely precisely. Now, let's go one step further, and let's look at the formalism for quantum clocks in a classical spacetime. So this is the line element of the in some classical metric field. And let's take a clock. One important distinction that we always have to keep in mind when we talk about quantum clocks is the different behavior between the internal degrees of freedom and the external degrees of freedom. So the internal degrees of freedom are the track of how time, while the external degrees of freedom are the ones that tell us where the clock is in the gravitational field. So the external degrees of freedom are not going to give us information about how the time ticks. What will give us information about the time is the behavior of the internal degrees of freedom of the clock.
Excuse me, can I ask a question?
Yeah.
Because it's going back a bit. I'm wondering what made the superposition of masses problematic. It sounded like people saw this superposition of masses and says, hey, we need the superselection rule to get rid of it. Like, what made it problematic versus like energy, right?
What do you mean? What made it problematic versus like energy?
Well, why? Okay, so the reaction to seeing a superposition of masses was saying we need a superselection rule to get rid of it. But then if you do the same calculation and see a superposition of energies, it's the same reaction that, hey, we need a superselection rule to get rid of this superposition of energy, right? What is the difference?
Yeah, the difference is that so the cyclic transformation that I showed you with translation is actually a composition of relativistic symmetries, so Galilean relativistic symmetries, because also like in Galilean relativity, this is a symmetric, it's like a symmetric, it's group theory, also that it's a different group from the special relativistic group, but it is still a group.
So it should have been an identity operation.
Yeah, exactly.
Right. Okay. Is it just ab initio? Are they all commutative and stuff?
No, they're not commutative, but they expected a cyclic, since I was translating by A, boosting by V, translating back by A, boosting back by minus V, then they expected it to be something that should not be observable, because in principle, I should go back to the same point, but then this is not the case. And in group theoretical terms, this means that the Galilean group of inertial transformations should have an additional generator, that is the one that is proportional to the mass Casimir. So M times the identity. But physically, this means that the mass superselection rule is something that is allowed, and it's a remnant of special relativity.
Okay, yeah.
For internal energy, you don't have the same problem, because you're not applying a sequence of cyclic symmetry transformations. So you just assume that you're doing something to the system actively, right?
Okay. Yeah, I think I get it now. Thanks.
Welcome. There's another question.
Yes. So since you're going back to the same, it's very similar to like the parallel transport we do in general relativity in Riemannian geometry, right? So is there anything like a since we're talking about group theory, is there any holonomy associated with these things? It's a very abstract question. So,
yeah, I don't know.
okay, so
I don't know. I've never looked into this aspect.
oh, okay, that's all right. Thank you.
Okay. So, okay, so now let's take a clock and let's choose the rest frame of the clock. And in this, so in the rest frame of the clock, there is basically no motion that is associated to the external degrees of freedom of this clock. So all the evolution is given by the internal degrees of freedom of the clock. So, and the time evolution parameter is I forgot some IH bar here. So the time evolution parameter is the proper time of this clock. So the internal energy evolves, the internal degrees of freedom evolve according to the internal energy of the clock in a time parameter that physically corresponds to the proper time of this clock in its rest frame. Now, imagine that we want to to change the reference frame from the rest frame to some laboratory frame, where the clock has some, instead, external dynamics of its external degrees of freedom. So basically, this means that the clock is moving. Now, the way we do that is to just change from the proper time to some other coordinate time, and then here we need to multiply the Hamiltonian of the clock by this tau dot, where this tau dot is the derivative of proper time by the coordinate time that we're picking. And formally, it can be written in this way, where this is the metric. And so basically, you see, it's just basically this line element derived by the dx0, that is the t. And so basically this depends on g, and it also depends on the velocity of the clock. So we will have different terms according to like how this clock moves. Okay, but then we are not yet happy, because here we still only have the internal only the internal degrees of freedom. We are not really considering the Hamiltonian associated to the external degrees of freedom. So how do we do that? We need to take both into account, and then this means that we also have to add the Hamiltonian of the external degrees of freedom. However, the situations in which we are interested in are situations in which, for instance, we send the clocks in an interferometer, so in which the clock basically in each arm of the interferometer almost follows a semi-classical trajectory. So a trajectory that we can roughly approximate as a classical trajectory. So a useful description of this situation is to take a path integral approach, where we have some external external action that is associated to the external degrees of freedom, and then we can simply evaluate this tau dot in the classical word line, basically the semi-classical word line of the clock in some interferometer. So, and this is an approximation, of course. It simplifies the calculations. It's not the most general thing you can do, of course, but for now, let's stick to that. I see that there are some questions. So I don't know. So there is a first question still about the superselection rule, but I don't know if. So the answer is basically the same that I gave to the previous question. I don't know when this was asked, if it was asked before or after.
It was asked after, but yeah, if it is not urgent, then we can discuss
Okay,
about
we
it
can,
during the break.
if there are still doubts, we can discuss later. And then there is another question, what are the sources of the external Hamiltonian? It depends on the physical situation. So for instance, we will typically have a kinetic term that is, say, if the particle is slow enough, it's p squared divided by 2m. And then we can have some external potential that can be, for instance, the gravitational potential, so the Newtonian potential, or also some other potential that we just put in the lab. For instance, if we want to constrain the motion of this clock around some specific trajectory, typically the Newton potential will not be the only thing that is there. We will need a potential, for instance, if we want to keep the clock on a table or at some specific height, we will have some electromagnetic potential that keeps it there, or some some normal reaction to the to keep the clock at a fixed height.
Sorry. But G mu is taking care of that. That interaction part, right?
Well, it can. It does not necessarily do that. So it really depends on your description. So because also in the Hamiltonian picture, G mu nu does not immediately enter in the description. So it really depends how you define it.
I'm guessing the scenario is like I'm starting with the quantum clock and I'm in a curved background. So I understand the lab frame thing, the evolution, written in a T frame basically. But I don't know what other potentials can be affecting my system now.
Well, for instance, so do you agree that if you put the clock, say here on a table, then the clock here and the clock here, say you fix them at two different heights, these two clocks will measure two different times because there are different heights in the gravitational field, so they will be subject to a different gravitational time dilation. But then the potential to which they are subject, the external degrees of freedom, is one, the Newton potential that points downwards, the Newtonian interaction with the Earth, plus some vincular reaction of the table that does not affect the way the clock tells the time, but still it's keeping the external degrees of freedom at rest here.
It's to keep this at stationary, you mean I need external
stationary,
force.
yeah.
Okay. But the setup is simple that I'm in a curved background, right?
Sorry, I didn't hear.
The setup is that I'm in a curved background.
Yeah.
All right, thank you.
Is the dot tau h in the lab frame Schrödinger equation Hermitian? Like, aren't there ordering issues? Okay, good. So, yes, in general, there are ordering issues when so now everything, so I'm cheating a little bit because here, sorry, I'm using my mouse. You don't see that though. So here, this is a classical expression, so there are no ordering issues. Then if I had to fully quantize this in a general gravitational field, there would be ordering issues. But then I'm going back to a classical, to an action picture where here we do not have anymore any quantum operator. This is all like histories, like classical histories. I had just some overall possible histories of the particle. And then I'm saying that I'm taking, say, a saddle point approximation that where only the classical trajectories of the clock matter. And then I'm basically avoiding this problem because here inside, I'm just putting classical variables. I'm not putting operators anymore. And I'm saying that this coincides with the classical action. Just put in a quantum superposition. So that's one way of avoiding ordering issues. The other way to avoid ordering issues is to take an expansion, a perturbative expansion, which is usually the case in the Newton potential. This is like a Newtonian expansion of the gravitational field. And so in this case, if we just take into account the first order of approximation, then we will not have ordering issues again, because basically the G00 will be just multiplied by 1, that is dt by dt. And then we will have the metric, but the special metric is just going to be the Minkowskian one in the Newtonian limit. And then we will have some velocity that in principle would not commute with x, but at this level of approximation, you don't see that because you approximated the metric, the special metric as like -1. So you just take the Minkowski part. So that's another way of avoiding ordering issues. But in a general case, there will be ordering issues, and this is not solved. Okay. So I think that the questions are all answered now. Okay. Good. So now, okay. So this is what I was saying. In the Newtonian limit, we take this expansion so we basically the only non-trivial term that we have is the G00, and this is the Newton potential. And okay, again, the action of a particle in this Newtonian limit can be written, just taking this line element, as the G00 part minus x dot square divided by c. So here you see explicitly that no ordering issues arise, because this is just something that, so this depends on x, but here you just have x dot here, so this will become momentum, but this just in a sum with the x dependent part. So no ordering issues arise here. And in the end, you can expand this in 1 divided by c squared. So when all the quantities up in the numerator are smaller than c squared. And what you find is that to the first order of approximation of perturbation theory, then you have this term here and this term here. And if you look at it, this already looks very familiar to the usual Hamiltonian in just quantum mechanics. And actually, if you, from the action, you take a Legendre transformation and you calculate the Hamiltonian, then except for an initial constant that is mc squared, then you find exactly the Hamiltonian of a particle. Here, I still haven't quantized anything. So this is a classical particle in the Newtonian potential. Now, how do I add the clock? I want to quantize this Hamiltonian, and I also want to add the contribution of the internal energy to the mass. So a heuristic way of doing that, and there are more formal ways of taking that into account, but they lead to the same result. So I'm just showing you the simple version, is to take the mass and substitute it with the mass plus h operator divided by c squared. So I have to do that both in the velocity, so in the kinetic term and in the potential term. Then for what follows, we want to consider just particles that move very slowly. So we want to say that basically this term is negligible. So the contribution, the coupling between H and P is negligible. Already at this level, though, you see that adding a clock to the Hamiltonian of a particle of a quantum particle in the gravitational field leads to a coupling between the internal degrees of freedom of the clock and the external degrees of freedom of the clock. And then what I was saying before is that we want to neglect this term here. So the Hamiltonian with which we will work is just the usual kinetic term, p squared divided by 2m, plus the potential term in which, except for the mass, so the rest mass times the Newtonian potential, you also have a coupling between the Hamiltonian of the internal energy of the clock times the potential, the Newton potential. Okay. And yeah, so this is basically G divided by X. So that's the expression of this stuff. So now let's take this description and let's put it in a quantum interferometer. So now, what do we have here? So we have, this is a single clock that is in the gravitational field of the Earth. And this clock is sent in a quantum superposition of two different paths, where the lower path is labeled with gamma 1 and the upper path is labeled by gamma 2. So now, if you remember from the description of the interferometer that I gave you in the first lecture, then we will have the internal degrees of freedom of the clock that is our target Hilbert space. So the Hilbert space that we really care about, that we want to measure, and that will be the one to which we apply operations. Instead, the external degrees of freedom of the clock is the control for us. So it just labels the path that the clock is taking inside this Mach-Zehnder interferometer. And so we're not going to really do operations on top of it. We just keep it as a say bookkeeping Hilbert space, just to label the arm of the interferometer. And then initially we have this clock initialized in a quantum superposition of its two energy eigenstates, and we split the state of the clock in the lower path and in the upper path. After, so at the end of the interferometer, before the final beam splitter that we put here, we have a state that is gamma 1, so the clock being having followed the lower trajectories, with some time tau 1, and a relative phase gamma 2 tau 2, which is the time the clock tells just before the final beam splitter. So now this phase, we don't care about it so much. It can be any phase, the phase that is accumulated by the external degrees of freedom of the clock because they take a different path, some other experimental phase that I just want to add because of experimental reasons. It takes everything into account. But if you remember, then what we had to do at the end of the interferometer in order to see interference is to forget which way information, meaning I have to recombine these two paths. So the control Hilbert space, I have to measure in a basis that we say at 45 degrees. So in the example that I gave you on Monday, it was plus minus basis. Here it's just say equivalent, but just putting a beam splitter and mixing gamma 2 and gamma 1. And then I should see interference. What one sees, though, when one has the clock, is that we have this state of the clock evolved differently according to whether it went on the lower path or on the upper path. So this results in a loss of visibility that you can see as with this red curve. So now let's pause for a minute and let's look at what this loss of visibility is. So this is the state of the clock just before the final beam splitter. So this is tau 1 and this is tau 2. So it refers to the different time the clock is telling us just before we recombine the paths, just because it has spent time at different heights in the gravitational field. So if the time was the same, then here I would have 1. So perfect overlap between the clock in the lower path and in the upper path. So I wouldn't have any loss of visibility. As soon as the scalar product between the state of the clock is lower than 1, meaning that the state of the clock is not identical at the end of the interferometer, I start having a loss of visibility. And this is bigger the more I separate the states of these two clocks. So the more the trajectory of the clock in the gravitational field are different in the gamma 1 and gamma 2. At the same time, the complementarity principle in quantum information tells us that the distinguishability, so the which way information, is 1 minus the visibility. So basically, the distinguishability becomes bigger the more the state of the clock is different, basically, in the interferometer. So even though I had tried to forget which way information, because I'm recombining the two paths, I still have some information about where the clock has been that is encoded in the internal degrees of freedom of this clock. So the take-home message that I have is that the clock carries which way information in its proper time. And this is something that is useful for us because we can encode the information about where the clock has been in the internal degrees of freedom, recombine the external degrees of freedom, and read out the information about the clock in the clock degrees of freedom itself. So in other words, this is a thought, well, now it's a thought experiment, but they are trying to do that in the lab. This is a thought experiment that takes the principle of linear superposition from quantum theory. It takes gravitational time dilation. It tests it together in a concrete scenario that is an atom interferometer, basically. Okay, so this is, okay, so I'm really putting an emphasis on this result because I think it's very important to understand in which sense quantum clocks encode information about the gravitational field. And it's something that can be quantified, so that's very important. Okay, so now, non-classical spacetime. What happens if we instead want to put the clocks no longer in a classical gravitational field of the Earth, but in some other scenario? So the easiest thing is to take two clocks that are exactly the same and let them interact gravitationally. How does that work? So we still use this mass energy equivalence. So let's focus on this clock here. So this clock here will have some effective mass E0 if it's in E0, and some other mass, say M1 plus E1, if it's in E1. So the fact itself that this clock is initialized in a quantum superposition of energy levels means that we have a quantum superposition of masses for each clock. When we put a copy of this clock nearby at some distance, so this is just actually the same clock, it just represented, sorry, it's two copies of the same clock, just represented differently, then also this clock will be in a superposition of masses. So they will interact with each other, but fundamentally it will be not a classical, not a classical spacetime. Of course, it's very, very small, but still, it's a clock in a superposition of masses. So we can describe that actually very simply in an interaction picture, just considering the gravitational coupling of these clocks, where you see that this is just the Newton potential, where h divided by c squared is the effective mass of this clock. But this is a quantum operator. So that's the mathematical way of representing this situation. Very simplified, but still we can work with that because it's enough to extract the information that we need from this scenario. Now, let's start from an initial state and of the two clocks where we initialize each of these two clocks in the usual initial state that is a quantum superposition of the two energy eigenstates, and let it evolve with this Hamiltonian here. So what we obtain is, okay, so let's focus on the clock A being in energy eigenstate E0. So when this is in E0, then this clock here evolves according to its Hamiltonian and the interaction term. So remember that, so we are setting E0 for simplicity equal to 0 here. So here, this will just evolve according to HB, because HA, when applied to E0, will be 0. So I just, this term will not contribute. And so this is just the ticking of clock B when A is in E0. Now, let's instead consider A to be in E1. So when A is in E1, then we will have this contribution here, but also this contribution here of delta E. So instead of HA, I put delta E here. And so I will have an additional term here. And so the clock B will tick in a different way when clock A is initialized in E1. And I can quantify the difference between how the clock B ticks with this quantity here, that is the difference between this phase and this phase. Now, notice that I have focused on looking at clock B now, just because of an arbitrary choice, but this situation is exactly symmetric under exchange of A and B. So I could have done exactly the same reasoning if I had expanded this in clock B and then looked at how clock A ticks. Nothing would have changed. Now, we have seen that the precision of a clock is the orthogonalization time. So it is pi h bar divided by the energy gap. And we have also seen in the previous slide that I can quantify the disturbance that of clock B due to the presence of clock A with this phase, with the phase difference between the two cases. So if I want to look, so if I take the physical dimension of a time, then this is quantified in this way. It's G times the energy gap times T divided by C squared divided by X, divided by C squared times X, the distance between the two clocks. So now I have the precision of clock A and the disturbance of on clock B due to clock A. This leads to some type of uncertainty principle. I can multiply these two numbers and I see, yeah.
Oh, I can say a thing. All right. I'm a bit lost here. So there are two clocks.
Yes.
And it's like two masses, and E0 and E1 are two states, which are like, it's like two masses are in superimposed state, right? Yeah. So what is the second part of the third part of the Hamiltonian, which was written last to last slide, I guess? Yes, this one, G over C4X.
This is the gravitational interaction between the clocks. So basically, if you can recognize here the Newton potential, if you substitute MA and MB to HA divided by C squared and HB divided by C squared. So this would be the Newton potential. So it's basically exactly the same thing that I did here. Let me get it. So it's basically this substitution here, where I have, so here I would have the mass of the sorts inside, right? It's the mass of the sorts divided by X and times G, the Newton constant. So if I take this expression and I substitute in both of them, because I consider both particle and sorts to be like a clock. So I have a term that is MM, a term that is just H times m and m times h, which is not what I'm looking at. This is all first order. I want to look yet at the next level, so next order in perturbation theory, at the coupling between the two clocks, which would be hc. Maybe I can write it. So this stuff here would be, so let's say that this is 1, and this would be so m1, m2 plus h2 divided by c squared. And everything then is multiplied by g and divided by x. So basically what I have is m1, m2, m1, h2, h1, m2, and then h1, h2 divided by c squared x times g. And then we can look back at what we have here. And this is exactly this term. It's HA, HB, G, C squared times H. Is this clearer?
So overall setup is that there is some external potential, which
No,
is
this is just a Newton potential. It's basically the gravitational interaction between the clocks.
yes. But apart from that, in HA and HB, there is phi, which is because of some external source, right? Or Earth or whatever.
No, there's only there is only the two clocks. That's the only thing I'm considering here.
What is phi then?
Where is phi?
Yeah, so the Newtonian potential, which you wrote, right? Which is because of
It's the Newton potential where the source is a clock. The source of the gravitational field is the clock itself.
Okay, so all right. All right, let's go forward and let's see.
So basically, so the G0, the source of, so the linearized approximation does not only hold if I have the gravitational field of the Earth. This is just a very general approximation that I can do in for weak gravitational fields, and then I choose my source.
No, I understand that. It doesn't need to be Earth always. All I'm trying to figure out, like the one source will have effect on the other, and it will be like a very complicated system, I guess. I don't think this Hamiltonian will work, but all right.
Okay, maybe we can discuss this later because that's a longer thing. But this is the simplest Hamiltonian that gives you the effect. So we also had a derivation from QFT in the paper in the supplementary material. So if you're not happy, you can just look at the paper with all the supplementary information, and then you can write to me.
Thank you.
Welcome. Okay, so we get this uncertainty principle where the precision, so basically we have a bound in the product between the precision with which we can tell the time at one in A and how much clock B is disturbed by the presence of A. So this is a limit to the measurability of time for nearby clocks. So you cannot measure time in an arbitrarily precise way when you have two clocks that are nearby and they interact gravitationally with each other. So that's the fundamental effect that we wanted to bring out here. And of course, this is a ridiculously small number because it scales like 1 divided by c to the 4th. But I think that the emphasis is that fundamentally this effect is there. It's before the Planck scale, if you put the numbers. It's also before the creation of a black hole. So it's something that at least conceptually is there, and we should keep in mind. Now, I change a little bit the topic to move back to the clocks in the next slide. So this is something that I didn't have time to introduce in the first lecture, but it is a process matrix that has 3 parties, and this refers, so I just anticipated the name of this when I was telling you about the different levels of indefinite causality. And so this is a process that classifies in what I classified as the third level of indefinite causality, that is the causal non-separability. And it does not violate causal inequalities. So it's this third level that is below causal inequalities, but above causal separability. And this is a quantum superposition of causal orders. And the process matrix is usually referred to as the quantum switch. So here we have three parties, A, B, and C. And again, we have a target qubit and the control qubit. Now, if the control qubit is 0, so this labels the path, then we have that a system, the target qubit, is sent first through A, then unitary operator UA is applied to the target qubit, then it goes to B, and then it goes to C. But if the control qubit is 1, then the opposite happens. So first the target qubit goes to B, then it goes to A, and then it goes to C. And now we can put these two in a quantum superposition. So we have that we do not know, we have in a quantum superposition, the order of first A and then B, or first B and then A of this process. And this is what is referred to as the quantum switch. And then in the end, we have to measure in C. Again, you see always the same measurement, we forget which way information, and we will detect interference. And this interference pattern, we can calculate the signaling properties, and this will not be obtained as neither signaling from B to A or signaling from A to B. There will be some additional interference pattern that is a mix of the two orders. Okay. Then I told you about this because this is just an interferometer. So it's something that can be realized in the lab, has been realized in the lab in many different experiments by now. But I want to tell you about the gravitational version of the quantum switch. How is this realized? So we have always A and B, and then C is some faraway observer. And A and B have two clocks, so they have a clock each. And there is a mass, say that initially we put a mass on the left here. So now the mass will take the role of the control qubit. And then if the mass is on the left, remember gravitational time dilation, lower is lower. So the clock A ticks more slowly than the clock in B. So this is why I have this, I have more ticks here in B. And then let's take just for reference some time equal to 2. So some time equal to 2 for clock A is here, and time equal to 2 for clock B is here. And then we can really fix the distances between A and B and the geometry of our experiment, so that the initial velocity of this a quantum system, so that this quantum system reaches B for when TB is equal to 2, and A when TA is equal to 2, and we can make sure that this tau A equal to 2 is in the future light cone of system B. And then after this TA equal to 2, then the system is sent to C. Now, let's do the reverse game. Let's put the mass on the right. And now the situation is exactly symmetric. So we will have that clock A ticks faster than clock B. The mass is on the right, so we will have that the control qubit is on the right state, say if you want the qubit 1. And then first the system will go to A, then to B, and then to C. Now, the gravitational quantum switch is when I put these two situations in a quantum superposition. So I have a quantum superposition of orders for the system to first go to B, then to A, and then to C, or first to A, then to B, and then to C. So that's the realization of the switch in a gravitational setting. Now here I drew the Earth, but you don't really need to think about putting the Earth in a quantum superposition. It's enough to put a massive body in a quantum superposition that should not be as big as the Earth.
Okay, so I was sort of going to ask that because this is a fairly impractical way, unless you just like launch a probe with a Stern-Gerlach machine really, really far away and you shoot, then you somehow have to catch the particle on the other end, but that's very impractical. A lot of these things, maybe I can ask a more general question, which has been bothering me. A lot of these things, you say people are doing experiments, but is there a problem in terms of the effect size? Because we're talking about gravity, which is super, super, super weak, and we're talking about like c to the fourth, reciprocal c to the fourth size effects and stuff like that. How much does that figure into like experimental design?
No, so that I said for that particular experiment, this is not so for that particular effect, the experiment is not feasible. It's the numbers are ridiculously small. So that I said that when I talked about the
so there are some experiments that are just killed by practicality.
Yeah.
How much is that? How much is that a factor in experimental design? I guess is my question.
So, okay, for that experiment, I think we are pretty far from the current experimental resolution. Currently, clocks can test 1 part in 10 to the 20, and we would need definitely more than that to get that so 1 part in 10 to the 20. I mean, in the relative phase, and we would need definitely more to test a sizable effect in that. Thought experiment with the gravitational interaction between clocks. But the one that I showed you before in the gravitational field of the Earth, I think that, so there are groups that are experimental groups that are actually trying to do that now. So this is definitely not a futuristic goal to achieve. So
is that just like weather balloons and stuff like that, or?
No,
you're not familiar with that sort of thing.
Yeah, atom interferometry. So that's
Thanks.
that's something that people can, well, if they cannot do it now, it will be in 5 years, but it's not something that is unrealistic. So effect 1 divided by c to the second, this can be done. And okay. Okay, so that's for what concerns the gravitational quantum switch. Now, this is, okay, maybe we can do a break just after this slide to ask other questions. But so another quantum information typical question is who writes the quantum state? So whenever we have a quantum state, we always assume that there is someone, some agent, some observer who can actually write down this quantum state, for whom this quantum state is meaningful. So whenever we talk about these clocks that are either in classical spacetime, non-classical spacetime, these clocks that are interacting one with the other, who is it that can actually see that quantum state? And the answer that we usually give is that there is always a faraway observer picture. For instance, for these 2 clocks that are interacting, someone who is so far away for whom basically if these 2 clocks are in E0 or in E1, it doesn't matter to him. He can just write down some Minkowski metric and all the fluctuations are far below his experimental resolution. And so he can just use the Minkowski metric to write down t, to write down x, and to write down the state of the 2 clocks together. But this is somehow an unsatisfactory picture because this is not always practical to have somebody who is far away, who is sending light signals and checking when these light signals come back to him, and like doing some operational picture to check that actually the state is actually the one that he thinks it is. So something that we would like to have is instead some quantum clock local picture. So saying, can I actually go to the frame in which this clock is and actually see how this clock is telling the time? can I stand on a different clocks and describe the quantum dynamics from their point of view? And that's the topic of the rest of this lecture, which is how do quantum clocks tell the time? So we'll now try to see if there is a way to make sense of the perspective of the clock and how this clock tells the time. And so I think this is a good moment to stop for questions.
There is one question in the Q&A from you.
When you talk about realizing the quantum mechanical switch in the lab, I am somewhat confused. My understanding is that we cannot set up a physical indefinite causal order in the lab, i.e. we cannot set up a superposition where A is in the future of B and B is in the future of A, though there are other scenarios people argue are equivalent to the quantum mechanical switch, but it is uncertain whether they are physically equivalent. Okay, so that is a big debate in the quantum causality community, whether these, okay, just to give some background to everybody. So all the realizations of the quantum switch are in a quantum optics setup, basically. So it has been done using linear optics. So in a like photonics, if you want, like, so for instance, photonics lab. So you have a laser, you send, you build an interferometry in the lab, and then you can have the system going first to A and then to B, and then at the end port, and then vice versa. So of course, in this case, you do not have that this photon reaches A and B at the same time in each amplitude. So if you want, if you draw this in a space-time picture, then you have that the first time it reaches it at some time T1 for the experimentalist, and the second time it reaches it at some time T2 for the experimentalist. So there are different views of, so for instance, how many times have I used the gates? This is a typical question that is asked. Or how many events are there in the quantum switch? And there are different answers in the community. So some people say that there are 2 events. Some people say that there are 3 events. Some people say that there are 4 events. And so I do not want to take any perspective now. So there are different, so you should just be aware that there are different opinions, and that there are different also resolutions of this. So one idea that I personally like is, but this has not been realized in the lab as far as I know, is to have some type of like memory added to the quantum switch, where you register every time the switch receives a quantum state. So how many times basically each local lab, A or B, receives a quantum state. And then you have this counter, and at the end of the experiment, you're going to look at the counter and see how many times it has received the state. And then this counter would tell you how many events there are. So that's a very operational way of resolving this this problem. Still, some people would not be happy because they would still want to count the event in space-time. And so in space-time, you have 4 events. Now, in what follows, I think, so I will give you some clock perspective where you can reduce to, say, at least 1 event for each, if you send it in 1 clock, and then you would see the other event, the other part is delocalized. So there are also some non-space-time implementation of this in terms of time delocalized subsystems, for instance, where you would just count 1 event for 1 clock and then 2 events for the other. And so that would lead to saying, okay, there are 3 events. So there are really different opinions on this topic. They're all valid perspectives. I would like to settle this with an experiment with adding a counter. And in this case, I guess the counter will tell us how many events there are. But yeah, if you ask different people in the community, they would give you different answers. And some people would tell you that the only real implementation of the switch is in the gravitational picture. So I think it really depends on your philosophical standpoint in this case.
I have a question.
Yeah.
So you mentioned at some point this mutual disturbance, this product of two different times and well, constants, and it gives you something. So is the physical meaning of this that there will be a minimal length of time that you cannot measure further?
Yeah. Yeah, exactly. So actually, it's very unsurprising also here, because basically that's so if you look at so this has h bar g c squared. So somehow you can get the Planck time out of this, and that's also really not surprising because basically the Planck units are pretty much the only thing that you can get when you have h bar, g, and c together. And
okay.
So yeah. Yeah,
but it is very nice to get the Planck time from an actual physical, a physical experiment, right? Okay.
Yeah.
One more comment about. Yeah. So these two clocks are of comparable masses, I guess, right?
Yeah, we assume that they are the same, but it's not necessary to assume that they are the same.
But, you know, the Newtonian approximation which you're using there may not work at all.
Why?
I mean, Newtonian limit only works when you have one mass which is very high and the second is very low and you're very far away from the source, right?
No, here you're just taking a post-Newtonian approximation and then reducing it to a Newtonian approximation, and you can consider two masses. And that's
whatever you start with, you will end up in G mu, right? And the structure of two comparable masses, if you keep, you can't write a metric for that. And once you can't write a metric for it, obviously you can't reduce it to Newtonian limit, right? We don't know the structure of G mu for two black holes merging also, right?
We're not talking about black holes here.
I know, I understand, but if two masses, if you have of comparable size, you can't write the metric, and obviously when you go to the Newtonian limit of that.
You are telling me that you cannot write down the metric field of any interacting particles.
You can't write, yes.
No,
we don't have a solution to that.
And interacting particles in the linearized regime, we know it.
No, start with two particles of same size, right?
You can check any book that has the post-Newtonian approximation, and you will find, even in the Goldstone book, you will find the metric field, the metric that is sorted by n particles in the linearized picture. You just take that.
Very far away from the source, I guess. Not very close to the source, right?
Linearized regime, I said.
But linearized regime won't work there, I guess.
Why? It works in the solar system.
Exactly, solar system, it works because.
But we are not thinking about black holes here.
No, I agree. But what if the masses are of comparable sizes? There's no way you can write a metric, I guess. And if you can't write a metric, obviously going to the Newtonian limit doesn't make sense.
As long as you are in the linearized regime, you can. Just take the Goldstone book.
All right, I still doubt, but all right.
Landau-Lifshitz also Landau-Lifshitz. It's there. Perturbation theory and particles in perturbation theories as sources of the gravitational field, and you can write it. You can write it down. It's perfectly doable.
I mean, all right. I can discuss it later. Anyways, I must be interrupting you.
Okay. Okay, so now let's go to the perspective of quantum clocks. So let me just review. So one of the formalisms that we like a lot in this community is the Page and Wootters formalism. And this is, so it's pretty old, 1983, and by Page and Wootters. And it was conceptually inspired to the Wheeler-de Witt equation in quantum gravity, but it is different, of course, because we're not talking about the wave function of some constrained gravitational theory. Like it doesn't come from the Hamiltonian formulation of general relativity. It just it's inspired in the sense that they took. So initially, they considered the clock and the system. Now you can just promote everything to be a clock, and it works equally well. And then you just focus on one of the particles. So let's just start with considering two different particles, A and B, and writing down this. So I'm going to spoil it, this constraint. So. And let us assume that it just has this form. Now, you can view this as the energy, as the Hamiltonian of these two A and B clocks. And then you also introduce some time operator, TI-HI, that has standard commutation relation with each of these H. Now, let me just add, since this question always comes up, that we know that you cannot have a time operator, that if you have a Hamiltonian, then you have a Hamiltonian that is not bounded from below. So how can this be a Hamiltonian? Or how, if you want to bound this Hamiltonian from below, how can you have a time operator? True. So the operational way in which one can think about that is that, so this is usually considered as XMP. So it's really, they span the whole, like they have a full spectrum. But what you can do in order to give a more operational flavor, more physical flavor to that, is to take an n-level Hamiltonian. So you have n levels that are separated by some energy gap. And then this, of course, leads to a time operator that is not perfect, but that still it's reasonable. And then in the limit, n going to infinity, this becomes the continuum Hamiltonian and the time operator that is canonically conjugated to that. Then you know that n going to infinity limit is not a physical one, that if you really want to consider a physical limit, then you should restrict H to be an n-level system. But since the calculations get harder, then for what concerns the following discussion, we can just stick to the infinite limit of H and T. But we know that as soon as we want to go back to physics, we have to restrict to n-level systems, where n can be arbitrarily big. Okay, so once we have this set up, then the physical states are obtained similarly as in the Wheeler-de Witt equation, as those that when applied to the constraint give 0. And then this can be solved formally by taking this operator here applied to an arbitrary state of A and B. So this state solves the constraint because if you see, I can integrate over tau, and this is a delta of C. So it ensures that this state here solves the constraint. And in addition, this is called also a timeless state sometimes. And the reason why it is called a timeless state is that, so if you naively interpret this operator C as a total Hamiltonian of A and B, then you can just apply the usual dynamical operation, like propagator, to the physical state by some time tau prime, and then you just expand this thing here as so you basically expand the psi phase in this way, and then this should be a minus. So you get tau minus tau prime, and then you can just change the integration variable in the from tau to some other parameter, and then this gives you exactly the same state. So basically, this state does not evolve in time, if you naively interpret that as a Hamiltonian. However, we can recover some dynamics. In which sense can we recover some dynamics? So by conditioning on the state of a clock at some time A. So when we take the scalar product of the physical state by some time t for clock A, then we find the state of clock B at the time t that is stalled by the clock A. And if we apply, so let's take the physical state C psi equal to 0, and let us condition this for this with this time t for clock A, for this cat. Now we know if these have a standard commutation relation, in the t basis for A, this operator here is represented as the time derivative of as basically d by with some IH bar, it's d by dt. And this instead is just transparent to clock A because this lives on a different Hilbert space. So if I do that, then you see that I recover the Schrödinger equation when on clock B. So here I have a dynamics when I want to look at clock B from the perspective of clock A. So in this sense, the dynamics emerges from the correlation between these two clocks. I do not have a global dynamics of these two quantum states, but I have a dynamical evolution when I look at one clock from the perspective of the other. And then I can just use a resolution of the identity for the physical state. And I can write the physical state in this way, where I name this as history state, because I have the whole history of time as in clock A, and then to each time at clock A, I can associate some state psi of t for clock B. And this is what is represented here in this picture. So for every t0 that I pick for clock A, I can have some psi of t0 that lives in this subset of the total Hilbert space for clock B. Here it's just named S, but it would be B here. And okay, so this is the Page and Wootters formalism. Then one usual problem that arises when we have this constraint description is that of observables, because usually observables are considered as the ones that commute with the constraints. But you see that since the constraint is HA plus HB, as soon as I include some T for A and B for the as an observable, then this will not commute with the constraint. So now there have been several possibilities in the literature to solve this problem. Here, I want to consider something that was discussed in these two papers here, which is basically a purification of the measurement. So instead of imagine that I have two clocks and some system S that I want to measure. Then I add a measurement system M that interacts with this system S, and then I record the result of my measurement in the measurement device. So this means that I have to modify my constraint in this way. And if I do it in this way, I can make sure that this observable here commutes with the constraint, and the measurement on M will not be, so basically the measurement device does not have some other Hamiltonian that I add here. Now let's analyze this constraint. So this is the previous constraint that I had without introducing any measurement. So, okay, so this is a simple case in which I haven't added any interaction between the clocks, but I can do that. So in this case, I wouldn't have this term. But so basically, this is telling me that the time of measurement is controlled by the clock 2. So basically, the measurement is switched on at some particular time when clock 2 tells me that it's time equal to Ti. This is, if I add the interaction between the clocks, I can also take into account some time dilation factor when the clocks interact, for instance, and we will see how this arises in the next few slides. And here, instead, I have some observable on the system and on M. And here, so the trick is that I'm just updating the state of my measurement device that is not evolving. So it doesn't have any Hamiltonian that is added here. So basically, this does not bring me out of the constraint surface. So that's the trick that one can use in order to define observable meaningfully here. Now, what happens if if I want to add some interaction? So basically, this measurement scheme that I added, that I had here, I wrote it in a more general way than what was needed, for strictly speaking, for this constraint here, because it can also take into account the next case, which is when I add interactions between the different clocks. So here I have a system of some n clocks, and I want them to pairwise interact, and I assume that this interaction is gravitational. So I could put anything, but here I'm just choosing it to be some gravitational interaction of the type of the two clocks that I was writing before. And then still, the reason is exactly the same. I have some, this is a constraint. I choose my physical state in such a way that the constraint applied to the physical state is 0. And then what I want to do is I want to take the perspective of one of these clocks, say clock I. So I want to describe the state of all these clocks from the perspective of the I clock. And I do that exactly in the same way I was doing that in original Page and Wootters. So I just take the sandwich of the physical state with the state Ti of clock I. And I will get here the state of all the other clocks as seen from clock I at time Ti. Then I can do the same for the Hamiltonian. So I can just take this, I can just take basically Ti here, the scalar product with Ti here on the physical state, and I will find this equation here. Now you see, this is in principle a little bit more complicated than what we got in the simple Page and Wootters case, because here I still do not have a Schrödinger equation, because I have this operator here in front of how the state evolves, and some Hamiltonian here. So what I have to assume is that this lambda, this coupling, is small enough so that I can invert this equation, so that this doesn't have any 0. And so I can safely invert it without running into any divergences. And by the way, a model of interacting clocks inspired to Page and Wootters was also done by Alex Smith and Mehdi Ahmadi in this paper here, and I wanted to encourage you to read it. It's a different model. They have a different type of interaction, and they find a non-local Schrödinger equation in time, so some Markovian dynamics. And you can check it out. It's different, but it's an interesting result. So if you invert that, then you find instead a Schrödinger equation where you have this factor here due to the basically gravitational interaction between clock I and all the other clocks, and some other Hamiltonian here. So the result that we found in this case is that first we can recover so assume now that the clock that you're picking is some clock that is far away from all the other clocks. So basically, this is something that will go to 0. So this term will go to 0. And we recover exactly the clock Hamiltonian from the faraway observer description. But we can also decide not to send this clock, this quantity to 0, and this will describe the clock Hamiltonian from the local clock perspective. So the thing that we couldn't do in the case when we had the limits to the measurability of time for nearby clocks, because we always had to refer to the perspective of some faraway observer, here we can do it by just taking the perspective of one of these clocks. Then we found also some relative localization of events and some implementation of the gravitational quantum switch. So the last thing that I wanted to tell you today is how these two arise, and I will just do the case of the gravitational quantum switch, that is the more complicated one, but you can look if you don't have the gravitational quantum switch and simply just this Hamiltonian, it works exactly in the same way. So I'll just do it for the gravitational quantum switch. So just as a reminder, this was the gravitational quantum switch. And from the C was the faraway observer. In this picture here, we can just write the gravitational quantum switch using this constraint, where this phi I is basically the Newtonian potential of the Earth in the where basically the position of the Earth can be left or right. And this is the only, so in this case, the Earth in a quantum superposition is the only body that is the only source of the gravitational interaction. And I'm saying Earth here, but again, this can be any quantum system that sources a gravitational field. And then we want to apply these operations when the time of is T star, so in this case 2, both for clock A and for clock B. And so what we have to do is to activate basically this local operation on the system when the two clocks tell me that it's time, either tell me that it's this time T star that is 2 in this picture. And I also need to include, since I have some gravitational field here, this is a time dilation factor. So that's it. That's all I need to do. And now I can take the perspective of either clock A or of clock B simply by conditioning on the time as measured by clock A or the time as measured by clock B. So let's see what we obtain, or also clock C, by the way, because it's also meaningful to do it from the perspective of the faraway observer. Now, if we take the faraway observer point of view, and this Hamiltonian here, sorry, I just changed slides, didn't mean to. Okay, then what we obtain is that, so if the mass is on the right, we have that A, the operation in A happens at some T star minus delta, and the operation in B happens at some T star plus delta. So A is before B. But if the mass is on the left, then B happens at some T star minus delta, and A happens at some T star plus delta. So B is before A. And you see these two operations, if I look at A, so A is in a quantum superposition of happening at T star minus delta and T star plus delta, and B is in a quantum superposition of happening at T star plus delta and T star minus delta. So, and this coincides with the usual description of the gravitational quantum switch from the perspective of C. But now let's take the perspective of A. So from A's perspective, instead, if the mass is on the right, her operation happens at some T star. And if the mass is on the left, it happens at the same time T star, as it is correct here. So you see that the operation in A always happens when the clock A tells me it's time t star. So this is perfectly consistent. But now let's look at clock B. Clock B tells me that when the mass is on the right, the operation happens at some t star plus epsilon. So again, B is after A. So that's exactly the same as for the faraway observer. And when the mass is on the left, instead, clock B still happens before clock A at some t star minus some quantity epsilon. So what I find is that we have indefinite causal order of the operations. The fact that I have an indefinite causal order is the same regardless of the perspective that I'm picking. I can take the perspective of C and the perspective of A, and still they will tell me that the order of the operations is in a quantum superposition. But the relative localization of the operation changes according to the perspective of the clock that I'm picking. If I'm picking the observer in C, then the operations are just delocalized in time. If I'm taking the perspective of A, then A happens at some t star, so it's localized, and B is delocalized. And it's symmetric if I take the perspective of B. B will be localized in time, and A will be delocalized in time. Okay, so that's all I wanted to tell you. So as a summary, what I've been arguing for in this lecture is that quantum clocks are a powerful tool to test the interface between general relativity and quantum theory. The simplest clock is a two-level system, and fundamentally, I have to take into account the mass energy equivalence when I couple it to the gravitational field. In classical spacetime, quantum clocks can encode information about their position in spacetime, while in non-classical spacetime, we have seen the limits to the measurability of time for nearby clocks, the relative localization of events, and the relation to indefinite causal order. So thank you very much for your attention.
Thank you, Flaminia, for the very nice lecture and review.
Thanks.
We have time for questions as usual. The chat is now open to everyone, but we encourage you to ask or raise your hand, and then we can unmute you and you can ask a question, please. Alicia?
Well, yeah, while everyone else prepares their questions, I have one. So you introduced this constraint and you called it a constraint, but well, constraints usually come from some symmetry in the system, right? So what symmetry do they correspond to?
So exactly, if you want, this I cannot find it, wait. Okay, so if you want, what you could see here is conservation of energy, of the total energy of the system, if you want.
Okay. Mm-hmm.
Yeah, and in this case, so I don't actually know if they had this in mind when they came up with this, or if they just tried to come up with some more operational model that was conceptually inspired to the Wheeler-de Witten equation. I do not know what they thought, but the way I see that is like conservation of total energy.
Yeah. That sounds a lot like Wheeler-de Witten. Yeah. Okay.
Do we have any other questions in the chat? I guess you were quite clear in the end.
Oh, there's a raised hand.
Hello, can you hear me?
Yeah.
Okay, so first, thanks for the talk. All those lectures were very nice, very clear. So I happen to be working inspired on many of these works that you've been showing on the last 2 days. In particular, I was curious about something you showed in slide 25.
Here?
Yeah, exactly. There has been a work by Haranov and recent collaborators where they consider a system somewhat similar to this. It's two clocks with a gravitational interaction between them. And they argue that generally for those kinds of situations, when you allow the particles to be spatially delocalized, that this Hamiltonian that you get on the right-hand side is actually not Hermitian because, you know, the Hamiltonians in the different two parts generally do not commute. And then that leads you to non-unitary evolution for your system. Well, in respect to the clock that you're picking. I think, well, I don't know if you know of this discussion and if you have any thoughts or comments on that. I was curious to hear about it.
Yes, so I think we even had some email exchange with them about that. And I do not remember the conclusion of the email exchange right now. But I think we sorted it out somehow. Yeah, so sorry, I don't remember again. But if you write me an email, I will try to remember, and I will get back to you with some answer. I will look back at the paper.
Just in general lines, you sorted it out in the sense that you recover unitarity, or it's just the non-unitarity wasn't a problem, or? So
in what is true, and that's something that I think we also comment on in this paper, is that we do not expect unitarity in the most general case.
Okay.
So that was along the lines of what we were thinking. But I don't remember in this specific case of this paper how we ended up the discussion.
All
but
right.
If you write to me, I can tell you more. I will refresh my memory.
Okay, thanks. And thanks again for all the lectures. They have been wonderful.
Thanks.
Okay. I guess we have no more questions. I mean, we had also quite a few discussions during the lecture, so I think that's completely fine. Okay, so I guess we can end it here, and we resume it tomorrow with the final lecture by Flaminia. Thanks again, Flaminia, and thank you everyone for joining in today.
Thank
Thanks
you.
a lot.
Thank you.